As Aidan said, I'm Peyton, and today I'm going to be giving you an overview of my engineering capstone project, nanoparticle-based biomonitoring of per and polyfluoroalkyl substances, also known as PFAS, or in other words, why we should care about PFAS and how to measure them. So first, I'd like you to think back to how often you get takeout, coffee. I know with the pandemic, it's pretty hard to avoid these to-go containers, and my consumption of them has increased dramatically. The reason we care about this is because all of these compounds and products have PFAS. So what are PFAS? PFAS are a class of man-made fluorochemicals found in a wide array of products from nonstick cookware to raincoats and waterproof hiking gear to stain removers because they have the really useful chemical property of water resistance. So they're the primary compounds in those nonstick coatings. However, in addition to all their really useful chemical properties, they also have some pretty harmful ones. They have earned the nickname forever chemicals because they are not biodegradable and therefore persist for a long time in the environment and can be found in our drinking water. Additionally, they have bioaccumulation capabilities, which means they stay in our body and compound because we cannot get rid of them. And these PFAS compounds have been linked to detrimental health effects like liver cancer and thyroid conditions. So because of all of this, it's important to be able to measure them. And so there are some monitoring systems already in place. So similarly to the fact that they now have biometric scanners at the airport that can look at your fingerprint to identify you, scientists can use an instrument called the mass spectrometer to generate a chemical fingerprint to be able to identify these different molecules. And so there are some organizations in the US, like the EPA and the CDC, that do have these monitoring methods for these PFAS compounds in both our drinking water and some human samples. However, they are really costly to perform and only a select few laboratories with specific expertise and equipment can actually do them. So a more efficient, easier method is required. That's where our solution comes in. So now that you know a little bit more about what PFAS are, why we should care about them and how to measure them, I'm going to go into our specific solution. So what are nanoparticles? What are our nanoparticles and how do they work? How we tested our nanoparticles and some future applications. So first, what are nanoparticles? So from the name, they are really small particles. They range anywhere from 1 to 100 nanometers in diameter. For reference, a nanometer is 1/1000th of a meter, or visually, a single human hair is about 1,000 to 100,000 times as thick as a nanoparticle. And the reason we're using nanoparticles is because they're really small, they have great high surface area properties, and they're just big enough compared to molecules, which are less than a nanometer in size, that we can have lots of interactions between molecules and our nanoparticles. So more specifically, what are our nanoparticles? So we designed a novel type of nanoparticle that we're calling molecularly imprinted magnetic nanoparticles, MINMPs, and I'm going to break that down for you. So molecularly imprinted refers to the fact that they can selectively bind compounds of interest. So the way we accomplish this is we have a molecule, in this case, one of our PFAS, and we can use this as like a cookie cutter to create perfectly shaped holes or binding pockets that have the same characteristics as our target molecule. So this way, our nanoparticles are selectively sticky for just our PFAS compounds. And the magnetic part comes from the fact that these nanoparticles have a magnetic core. So how do they actually work? So as I mentioned, we use those molecularly imprinted cookie cutters to create all of our binding pockets around the outside of the nanoparticle. And so when you introduce these to a complex solution, only the compounds that are very similar to those binding pockets are able to slide in and bind to our nanoparticles. And then since the core is magnetic, we can use a magnet to isolate these PFAS nanoparticle complexes from solution and get them alone. From there, we can take a wash step, which forces the PFAS to unbind from the nanoparticles. And once again, we can isolate the nanoparticles using a magnet, leaving behind only the PFAS that were originally in the solution to measure. So this is contributing to more easily monitoring system, because instead of having to scan for only the fingerprints that you want amongst hundreds of different compounds, we can isolate only the desired PFAS. So now that you've gone over kind of an overview of how they work, how do we actually test that they're doing what we need to do? So the first thing we had to do to accomplish this is we had to create a mass spectrometry method so we'd actually be able to quantify the levels of these PFAS in our samples. So the way we did this is basically I had to program what the fingerprint looks like for each of these PFAS molecules and let the machine know what it was looking for. So once that was accomplished, we could begin actually testing our nanoparticles. And to do that, we start with a concentration of known PFAS levels. This is called our stock solution. To this, we can add our nanoparticles and we let it sit for a little bit so that the nanoparticles can, or the PFAS can bind to the nanoparticles. And then we can use a magnet to isolate those complexes like before. But then this time we're actually going to extract what's called a supernatant solution. So this is the solution where all the PFAS that didn't end up binding to the nanoparticle reside. So then by comparing how much was not originally bound to the PFAS to how much we knew was originally in there, we can figure out what percentage of PFAS actually bound to our nanoparticles. And this is important to know because knowing the efficacy or the efficiency at which PFAS bind to our nanoparticles allow us to actually use these particles for real samples and be able to effectively mediate the levels. So if we know we have an 80% binding efficiency, then whatever our levels in actual samples are, we need to add 20% because 20% did not bind. So now that you kind of understand how they work, what are some applications of this? So one of the main applications we're looking at for the future is biomonitoring. This is important because, as I mentioned, PFAS accumulate in the human body. So understanding and watching the different levels throughout time and population will be important to better understanding both these molecules and the diseases they're connected to. So the way this would work is we could start with any type of biological sample. These could be blood samples, tissue samples, serum samples. We would add our nanoparticles to them and we'd follow those same steps I outlined in the what are the nanoparticles, where we let them bind, we isolate the complexes, and we elute off the PFAS. So those PFAS would be only the PFAS that were originally in these samples. So by knowing those levels, we would be able to effectively measure and track the number of PFAS in these various samples. So some key takeaways. I hope you learned what PFAS are and why they're important to study. They're everywhere. And we are exposed to them through many consumer products and through our drinking water. And while there are current methods for monitoring these compounds, they are costly and limited in location. So to address this, we've designed some nanoparticles as a more efficient means of monitoring PFAS in various types of solutions. One of these applications can be future PFAS biomonitoring to address the growing concern of these compounds in our population. I would like to thank my advisors, Dr. Joyce Wong and Sabra Botch-Jones, and a special thanks to Isabella Clare, Perkin Elmore, the Wong and Botch-Jones Labs, the College of Engineering, and the Kilachand Honors College. I will now take questions.